So we're going to begin our discussion of chapter 2, which again focuses on resonance, structure and function, and acid-base chemistry. And to really drive home this first point, let's start by looking at an example that showcases how Lewis structures are often inadequate to describe the structures of molecules. So again, this is the chapter 2 notes, which are found on Canvas. So when we try to draw a Lewis structure for the acetate ion, for example, we end up with a structure that looks something like this as our first pass. Now, from this structure, we can try to answer the question, which carbon-oxygen bond is stronger? Bond number 1 or bond number 2? Which bond, just looking at this structure, would we expect to be stronger?
One.
So at first glance, we would expect 1 to be stronger, as it has a bond order of 2. But, and this is really critical, both bonds are actually equally strong. They have the same length and strength. And this is due to resonance effects, where in reality, the electron density found in this bond is evenly distributed across all atoms participating in resonance. So rather than having a single or double bond, we instead have a quote-unquote 1.5 bond. And we're going to really unpack in this chapter drawing resonance structures and looking at how the resonance structures impact the overall structure that we observe, which we call the resonance hybrid. So we've seen a clear example about how we really need to pay attention to resonance, because it has a direct impact when we start to answer questions about bond strength, length, and the location of charge, the location of potential sites of electron deficiency or electron-rich sites where reactions can occur. So, the Lewis structures that we draw cannot predict or fully describe the actual structure of many compounds. So resonance structures are defined as one or more valid Lewis structures with the same skeletal formula, but a different distribution of electrons in bonds or lone pairs. So for example, for acetate, we had the first structure, and we can just as easily draw a second resonance structure where we're forming our double bond with the bottom oxygen. We indicate resonance structures using these double-headed arrows. So, although we're able to draw multiple distinct Lewis structures, the actual structure is a weighted average of all resonance structures based on their favorability. Further, the actual structure we observe in terms of bond lengths, strength, is a weighted average of all resonance structures based on their contribution. So what we actually observe is not any one of these particular resonance structures, but a weighted average of all the resonance structures. These resonance pictures are just that, pictures that can help us visualize potential ways that we can distribute electron density. none of these resonance structures are fully descriptive of our actual molecule. So, just like Lewis structures, favorable resonance structures that are major contributors will minimize formal charges, will in general satisfy the octet rule, place negative formal charges on electronegative atoms, and will place positive formal charges on less electronegative atoms. And opposite charges can be placed or should be placed on adjacent atoms if possible. Now, resonance is not just rotation of a molecule. So if I label these carbons 1, 2, 3, if I just rotate my molecule, with the same carbon numbering, this is not a resonance structure. Resonance requires a change in the distribution of charge and electron density in our molecule. So does everyone notice how in the resonance structure we have a different distribution of bonds between our 3 carbons, a different distribution of electron density about our 3 carbons? Does everyone see how these 2 structures on the left are resonance structures, while the structure on the right is just a structure obtained from rotation? Does this make sense to everyone? So just be careful and number your carbons. So in terms of resonance structure and the actual molecular structure, the actual structure we observe is a weighted average of all resonance structures based on their contribution. Now, one way that we depict the true structure as a weighted average of resonance structures, we can either use dashed bond notation or curved bond notation, where this dashed bond is indicating that we have electron density delocalized across multiple atoms, and we have a charge that is delocalized across multiple atoms. So that you can think of this as describing delocalized electrons. Another way that this uneven, this is an entirely different compound. So this is not acetic acid anymore. This is looking at the 2 resonance structures of what we call an enolate. Another way we can showcase this delocalization of charge and electron density is by using a curved bond connecting all atoms that are participating in resonance. So in this case, we're indicating a delocalized charge in addition to electrons that are delocalized across our 3 atoms. You can either use dashed or curved bond notation. Both are valid. And this is really starting to show how, and starting to describe how our electron density is distributed as a result of resonance. So let's unpack a little bit how does resonance actually function? So let's go back to our idea of pi bonds for a moment. Pi bonds are the overlap of unhybridized p orbitals perpendicular to the bond axis. So pi bonds adjacent to parallel p orbitals can overlap and generate an extended pi bond called a pi system. So for example, if we have adjacent double bonds, the p orbitals, which are engaging in a pi bond, can potentially overlap with parallel p orbitals engaging in adjacent pi bonds. And in turn, the overlap of these adjacent p orbitals can generate what is known as a pi system, which is a series of parallel adjacent p orbitals overlapping. We define conjugation. We define conjugation as the overlap of p orbitals in 3 or more adjacent atoms to form a continuous extended pi system, where a pi system is any set of adjacent p orbitals or pi bonds. Now, we can distribute our electron density throughout pi systems, not just involving double and triple bonds. We can also distribute electron density found in lone pairs. And to understand how this works, first things first, we need to take a look at our valence bond model. So ozone looks something like this. So, the reason why I spent so much time focusing on where are our electrons, what orbitals are electrons found in, is because it becomes really critical when we start to discuss resonance to figure out which lone pairs are localized and which lone pairs are delocalized. So we have our pi bond, okay? And let's just put some labels. Let's just put some labels for right now. Let's just put some labels. So looking at, let me make it so it's perfectly matching. There we go. So we have our pi bond. And for this leftmost oxygen, I'd like you to tell me, what orbital is this lone pair found in? What orbital is this lone pair found in? Is it found in a p orbital or a hybrid orbital? Let's answer this question. This is the centerpiece of beginning to understand acid-base strength. So to back things up a little bit, what is the hybridization of this oxygen? What is the hybridization of this oxygen?
sp2.
sp2, okay. So in the sp2 hybridization, we have 3 sp2 orbitals available and a p orbital available for bonding. In this pi bond, we've used up an oxygen 2p and an oxygen 2p orbital to form this pi bond, right? Is everyone following with that premise so far? So the lone pair, exactly right. Because we've already used up our p orbital for forming our pi bond, our lone pair, this lone pair on this leftmost oxygen is in an sp2 orbital. So then, can this lone pair participate in resonance? Can this lone pair participate in resonance? Is this lone pair in a p orbital? Is it able to interact with the pi system? So we just said this lone pair is in an sp2 orbital. So then, because it's in an sp2 orbital, can it interact with this pi system? Is an sp2 orbital the same thing as a p orbital? No, it's because this lone pair is in an sp2 orbital, it is localized. And it cannot participate in resonance. Okay. Likewise, let's do the exact same pattern of logic. Notice how in our orbital picture, the sp2 orbital and the lone pair is located clearly in sp2 orbital, and it is no way parallel or able to overlap with our pi system. let's look at this central oxygen just to make sure we understand this point. What is the hybridization of this central oxygen? What is the hybridization of this central oxygen?
sp2.
sp2, okay. So then my question to all of you is, this lone pair is found in what orbital? Where is that lone pair located? What type of orbital is that lone pair located in? Is it located in a p orbital or an sp2 orbital? Keep in mind that we already formed a pi bond with this oxygen. This is a really critical point, so don't be shy to share your responses in the chat so we can advance this discussion. So is this lone pair found in a p orbital or an sp2 orbital? Keep in mind that this oxygen, as it's sp2 hybridized, has 3 sp2 orbitals and 1 p orbital. And we already used this p orbital to form our pi bond. So we've used that. That p orbital went to form our pi bond. So then, where is this lone pair located? Where is this lone pair located? In an sp2 orbital. Exactly right. So this lone pair is also in an sp2 orbital, so we call it a localized lone pair. Now, we're not done here because this last oxygen is where we can actually do something a little bit interesting. So this last oxygen, we can propose that it's hybridized, or we can leave it as an unhybridized oxygen. So this is what our last oxygen looks like, okay? So in terms of bonding, we've used up one of our p orbitals to form a sigma bond. So this was used for our sigma bond, okay? This oxygen has some lone pairs, and we also have a half-filled orbital. And my question to all of you is, what can we do with half, where is this, so what I'm trying to convey to you here, the question that we're trying to answer in this section is, do we have a p orbital that is available and that can participate in resonance? Do we have a lone pair in a p orbital for this leftmost oxygen? Looking at our orbital picture, do we have a lone pair available in a p orbital? Yes, so let's draw that. Let's draw that out. So this oxygen has a p orbital containing a lone pair. So then, as a result, the lone pair on oxygen, this lone pair right here, is considered delocalized, and it can participate in resonance. So as a result, this lone pair can distribute its electron density across the pi system. So, in effect, the electron density found in our double bond and lone pair has now been distributed across the 3 oxygen atoms. And this lone pair can only engage in resonance delocalization because it's in a p orbital that's parallel to an adjacent pi system. Does that make sense? Does everyone understand why only this leftmost oxygen's lone pair can participate in resonance? while the other lone pairs cannot. A lone
Roughly.
pair can participate in resonance if it is located in a p orbital that is parallel to a pi bond or pi system. And as a result of resonance, this electron density found in our double bond and lone pair is distributed across all three of our oxygen atoms. Does that make sense? Does anyone have any questions on this discussion? Really don't be shy to ask. We'll be doing a lot of examples like this, hitting on this major theme. Is
I guess
everyone,
it's just a little rough right now.
is there a question that I can answer?
Not for me. Maybe just as we go along, will probably make more sense.
Okay, we'll draw a few more of these orbital pictures to help understand and rationalize whether or not a lone pair is localized or delocalized. Just really focus on thinking, what is the hybridization of my atom? And is that lone pair in a p orbital? So we can think about these pi systems and we can process these pi systems using MO or molecular orbital theory. So in molecular orbital theory, I'd like you just to recall the fact that we generate molecular orbitals equal to the number of orbitals combined. Since we combine 3 p orbitals, we generate 3 molecular orbitals. For each bonding orbital we generate, an antibonding molecular orbital is also generated. If you have an odd number of combined orbitals, a non-bonding orbital is generated. Since p orbitals are phased, a bonding orbital involves the overlap of p orbitals with regions with the same phase. Conversely, antibonding involves overlap of p orbitals with opposite phase. So, what do I mean by that? What do I mean by phasing? So let's suppose we have our 3 p orbitals. So each of these p orbitals have phasing. In an antibonding interaction, we have an overlap between regions of opposite phase. We call this destructive interference. So this would be known as our antibonding pi orbital or a pi star orbital. Does this idea look familiar to everyone? This idea of bonding and antibonding. We've just taken this one step further and we're looking at bonding and antibonding interactions across multiple atoms. We're looking at molecular orbitals now. So notice how we have multiple regions of opposite phase adjacent. This is known as an antibonding molecular orbital. In a non-bonding molecular orbital, what the non-bonding molecular orbital is trying to describe, is the presence of a localized lone pair. So in this model, we don't have a straight antibonding interaction as the atoms containing the orbitals of opposite phase are not adjacent, but we have a node centered around one of our atoms. So the best way I like to think of a non-bonding orbital is that rather than destructive interference, we don't have a significant amount of orbital overlap between our adjacent pi systems. And the way that I like to visualize, the way I like to think through this non-bonding interaction is it's essentially trying to describe that on one of our atoms, we have a localized lone pair. That's essentially what the non-bonding interaction is trying to describe. It's neither bonding nor anti-bonding. The next most important molecular orbital to discuss is the bonding molecular orbital. As we can see very clearly from our given picture, we have an overlap between p orbitals with the same phase. This is constructive interference, and it's a very stabilizing overlapping interaction. So in general, as we move up from the lowest to the highest energy molecular orbital, our number of nodes increases. And as a result, we have less overlap between orbitals of the same phase. We have more regions where there's no electron density shared between our atoms. In general, as you increase the number of nodes, the orbital energy increases as you have less overlap and less overlap between regions of the same phase and less stabilizing interactions between your orbitals. So essentially what we've done here is we've taken MO theory and we're beginning to use MO theory to describe the distribution of electrons about our entire molecule in our pi system. And from these MO diagrams, we can begin to describe and we can begin to understand the relative energy of our molecule, and we can begin to understand, by looking at the molecular orbital picture, potential sites of reactivity and modes of reactivity for our molecule. The molecular orbital pictures for our highest occupied molecular orbital and lowest unoccupied molecular orbital are going to be critical later on in this class to understand how different reactions occur in the presence of heat or light. So does this idea of molecular orbital pictures for pi systems make sense? Bonding, we have constructive interference. Anti-bonding, we have destructive interference. Non-bonding, we essentially have localization of electron density on one or more of our atoms. That's what non-bonding molecular orbitals are trying to describe. And the more nodes we observe, the more regions where we do not observe overlap between our p orbitals in our pi system, the higher in energy our orbital becomes. Does that make sense to everyone? Perfect. So let's talk about drawing resonance structures. How do we draw resonance structures? So first, electrons in conjugated pi systems are delocalized. So we want to avoid breaking single bonds when drawing new resonance structures. That would be counterproductive. You also want to make sure that you never exceed the octet rule for second row elements. Now, one of the actions that we can do when drawing resonance structures is we can move electrons shared in pi bonds to any atom participating in the pi bond. We note the movement of electrons using a curved arrow starting from the lone pair or the pi bond's source of electron density. So for example, in this case, we have a double bond, we draw our arrow, and we've moved our electron density to our carbon. In general, it is preferable to place negative charges on the more electronegative atoms and positive charges on the less electronegative atoms. So for example, in this case, we can kick our electron density from our double bond to our nitrogen and generate the following resonance structure. Just to make sure we're all on the same page here, what would the charge on carbon be? What would the formal charge on carbon be if we break this double bond? So just to visualize what's currently bonded to this carbon. So we have the carbon is bonded to a carbon, a hydrogen, and a nitrogen. So if we calculate the formal charge of this carbon exactly as drawn, what would the formal charge be? +1, yep. 4 minus 3 gives us +1. So we'd put a positive charge. And the nitrogen would have a negative formal charge. Okay, perfect. So this is one possible resonance structure that we can draw. Another possible resonance structure that we can draw would involve movement of our electrons in our double bond onto carbon. Oops, allow me one moment. Okay, perfect. So in this second resonance structure, we'd have a negative formal charge on carbon and a positive formal charge on nitrogen. Which of these two structures is preferred? The structure in the dark ink color or the structure in the purple ink color? Which of these two resonance structures is preferred? Which resonance structure places positive formal charges on less electronegative atoms and negative formal charges on more electronegative atoms? Yep, the purple structure. So this purple structure is preferred because we place our negative formal charges on the more electronegative nitrogen and a positive formal charge on the less electronegative carbon. Does that make sense? Any questions on this example? So what I'd want you to do now is to try and draw a valid resonance structure for each of the following two compounds. And then we'll discuss these examples in about 3 to 4 minutes. Make sure to use the annotate tool to share your proposed responses onto our shared course whiteboard, and I'd be happy to provide feedback. So let's focus on drawing at least one valid resonance structure for each of the two molecules and try to abide as closely as possible to our rules for preferred resonance structures. And remember, you can share your responses using the annotate tool by clicking the Zoom options tab, which is the little black tab in your Zoom view. And as one of the options, it'll show annotate, which will allow you to draw your proposed structure and draw your proposed resonance structure. So don't be shy to share your responses, and I'd be happy to provide feedback. And you can also submit image files of your drawn responses, and I'd be happy to look them over and provide feedback. And remember, when drawing resonance structures, it's best to start by using the arrow pushing notation, where you draw your arrow showing the movement or redistribution of electron density from our double bond to one of our atoms. Oh, are other students having trouble with the annotate tool? So we'll keep working on this example for another 2 minutes. Worst case, I'd like you to tell me which atom will have an additional lone pair. So I see in the chat that someone has written out a proposed structure for the resonance structure of acetone. So this is one of the students' proposed structures, just to make sure I'm interpreting it correctly. You have a resonance structure that looks like this. Okay, and if you have any other proposed structures, I'll try to draw them out in the chat and then we'll discuss. So this is one of the student proposed structures. And we'll talk about each of these structures in about another 1.5 to 2 minutes. If you can, I encourage you to try to draw using the annotate feature, as it provides me a way to give you in-time feedback. You can also unmute your camera and show me your structure in the camera pane, and I'd be happy to provide feedback for your proposed structure. Okay, we have another proposed resonance structure. So let's talk about this example and let's provide a little bit of clarification. So let's clear the drawings and let's first talk a little bit about the central rule of resonance structures, which is we can't break single bonds when we're drawing resonance structures. So I always like, as a first step, if I'm ever unsure, I like to draw out my single bonds, okay? So this structure shown here is not quite a resonance structure. This structure proposed here, I can draw this off to the side, is known as a tautomer. And in this tautomer, we've actually broken one of our bonds. So it's not quite a resonance structure, but it is a common form of acetone that is generated from a series of acid-base reactions and proton transfers. So we'll see this structure later on in this chapter, but it's not a resonance structure. It's a constitutional isomer, or more accurately, a tautomer, which is a species generated from a series of proton transfers. Now that I've drawn out my carbon-hydrogen bond, for resonance structures, try to keep things as simple as possible. We have our double bond. We can either move our electron density up to oxygen or down to carbon. Those are the only two atoms involved in our pi bond. So then, if we kick our electron density up to oxygen, we now have a lone pair on our oxygen, and our carbon has lost a bond, so it now has a positive formal charge. So this would be one valid structure for acetone. This would be one valid resonance structure for acetone. Does that make sense to everyone? So remember, in resonance structures, you cannot break single bonds and only focus on the pi system. You can move your electrons in your double or triple bond to one of the atoms involved in that bond. Keep things as simple as possible and take things step by step. Likewise, if we draw out our hydrogens, The only thing that we need to care about when we're drawing resonance structures are the two atoms involved in our pi system. So I'm just gonna highlight them. So I have these two carbons, right? And I can move my electron density in my double bond to any of these two carbons. Does anyone have a preference? The left carbon or the right carbon? Which one should we move it to?
Right.
Right, sure. So for right now, that would be a perfectly fine answer. And generally, when we have a double bond, there's no preference for which, there's not a huge preference for which atom receives the lone pair. We end up with a positive formal charge on our other carbon and a negative formal charge on the rightmost carbon. So this would be a valid resonance structure. By the end of this class, the best option would be the following resonance structure. If we had to pick major and minor. And that's just because, as a side note, generally we like to put positive charges on the atom with more carbons. But for right now, if you're just drawing these resonance structures, both of these structures would receive full points on the first set of quizzes and on the first exam. We took our electron density in our double bond and moved it to one of the two atoms involved in our pi system, or involved in our pi bond. Does that make sense? Is everyone more comfortable with this first step in drawing resonance structures? Can I get some feedback in the chat from everyone who's here?
Yep.
Perfect. Okay, so we're gonna add another rule. So we can also move electrons in p orbitals adjacent to pi bonds to form a new pi bond. So in this process, as a new pi bond is formed, the initial pi bond is broken and the electrons in that pi bond are moved to the atom not participating in the new pi bond. It's very wordy, but it can be distilled down into the following sort of visual heuristics. The electrons in the lone pair are pushed down to form a double bond. The electrons in the double bond are pushed up to give a lone pair. So we draw our arrows like so. So we push our lone pair down, forming a new double bond, breaks our previous double bond, and our electron density in that double bond gets moved up to oxygen, which is no longer participating in a double bond. Does that make sense to everyone? So in general, your electrons, when you push your electrons to draw resonance structures, they should move from one atom to an ending atom. Your electron arrow pushing notation should in general go in one direction. Does everyone see how we're essentially pushing electron density from nitrogen into our double bond and then up to our oxygen? Does that make sense?
Yeah.
Okay, and the reason why this works is that adding electrons to a pi bond or a pi bonding system will fill the anti-bonding pi star molecular orbital and break your pi bond. So this process of pushing electrons into pi bonds to break a pi bond and form a new bond can be repeated. So for example, we can draw a first resonance structure where we've kicked our electron density from our nitrogen all the way to one of our carbons. And then we can keep going and we can continue pushing our electron density to further delocalize our lone pair across multiple atoms. Does this make sense to everyone? Oops, let me be very specific here. Your ending arrow should point directly to the atom that you're forming the lone pair on. There we go. Does this arrow pushing notation make sense to everyone? Does this process make sense? Perfect. So let's test. Let's apply what we've learned. And I'd like you to draw at least 2 valid resonance structures for the following molecule. And we'll take about 3 minutes working on this example. And don't be shy to try using the annotate tool to share your proposed responses. Or you can unmute your camera and share a picture of your work, or you can paste a picture of your work into the Zoom chat, and I'd be happy to provide feedback. I want to give everyone some time to come up with their proposed solution, so that way we can compare when we discuss this example together as a class. And remember, you can always share an annotation by clicking on the black bar titled Meeting Options and going to the Annotate feature. And we'll discuss this example in about 2 minutes. And is everyone able to access the annotate feature? It's especially useful when you're sharing your proposed structures. So that way I can take a look and draw out some proposed structures. Worst case, you can also share your camera or screen with your drawing, and I'd be happy to provide feedback. And we'll discuss this example in about another minute. Oh, perfect. So we have 2 students who are able to use and share their proposed structure. Wonderful. So I see some pieces that are really good. I see some pieces that look good. There are just some small points that we can revise, but I really do appreciate that we have 2 different shared responses, as part of these structures look great. There's just one part that we need to pay a little bit more attention to. So let's talk about this. So first, when you're starting out drawing resonance structures, let's just draw out our hydrogens. Let's make this as clear as possible where all our hydrogens are. Okay, now that I've done that, following our rules, we can push our electron density into any pi system. So we have an adjacent pi bond. So we're going to push our electron density down to form a new pi bond. We can't push our electron density to this left carbon because it's saturated. We can't break these carbon-hydrogen bonds. Does that make sense? So when we kick our electron density down to form our bond, the electron density in our lone pair gets kicked up to the carbon and we generate a new lone pair. So this is our first resonance structure. And from the responses I saw, I do believe that students are comfortable drawing resonance structures. It's just a matter of doing each of the resonance structure parts piece by piece. So for example, in the first structure that I saw, the student very correctly noted that you can kick this lone pair down and break our carbon-oxygen double bond, and you end up with a structure that looks like this. So I really try whenever possible to keep my resonance structures as simple as possible when it comes to arrow pushing. I like to draw one arrow pushing step at a time. It keeps my thoughts organized and it keeps things from getting too messy. So, do these resonance structures make sense? So the first response that was drawn, it was almost perfect. It was almost spot on. They recognized this second step and they clearly understood this second step. It's just a matter of making sure for your first arrow pushing step, you push your electron density to form a bond adjacent to a pi system, and then your pi bond is broken. You can only move and redistribute your electron density in resonance structures. You cannot break single bonds. Likewise, in the second structure, the student very astutely noted out that there's another case where you can draw a resonance structure where if we kick our lone pair down on this oxygen, we can break our carbon-oxygen double bond. And that is also a reasonable resonance structure. It's not a major contributor, but it's certainly a reasonable structure to draw if you're asked to draw a resonance structure. So the pieces are there, and don't worry, resonance structures require a fair bit of practice. And I really encourage you to look over some examples and problems in the book before our next class session. And the plan is we'll continue this lecture in laboratory today, and we'll continue working through examples.